Kepler, can you say something? Do you hear us? Does anyone hear us?
I can hear you.
Okay, good. Okay, fine. Okay, so let's start. So sorry for the problems we had. Thank you so much, Yannick. So good afternoon, everyone. Welcome to today's seminar. It's a pleasure to introduce Yannick Barret, who just moved to Lausanne, Switzerland. Before moving to Switzerland, Yannick was a Marie Curie Fellow and an NVO Fellow in Leiden, the Netherlands, for several years, and also at MPA in Germany. He obtained his PhD in Cambridge in the United Kingdom, and he's going to tell us about satellites to intracluster light, the transformation of galaxies in groups and clusters. Thank you so much, Yannick, for accepting our invitation. The floor is yours.
Thank you very much. Yeah, thanks a lot for inviting me to talk to you about my research. Can you hear me properly, first of all, when I speak like this? Excellent. Great. That's good. So yes, I'll be talking about some research of mine that deals with galaxy clusters and the galaxies living in them. But I would like to start by really acknowledging that this is not work I've done alone. It's work done in collaboration with a large number of other people. And I should highlight in particular Observational, Richard Bauer, who sadly passed away last month, David Barnes, Claudia Della Vecchia, Scott Kay, and Rob Crane, whose input has really been invaluable for getting all this work done that I'll be presenting now for the next 45 minutes roughly. So I'll be talking about galaxy clusters mostly, so very large scales in the universe. And I'll begin by motivating in one slide why galaxy clusters are interesting to study and to look at. And in many ways, this picture really says it all in a way. This is one of the most massive clusters that we know about in our universe, Abell 370, one of the 6 Hubble Frontier Fields clusters. In total, there's more than 1,000 galaxies that are in total in this cluster. It's actually only a small portion of the central region that's shown here. But you can already see that it's a very crammed, crowded region of our universe with many, many galaxies standing very close together. And there's an awful lot going on in this image here. For example, you can see some of the galaxies look very strangely distorted into these giant arcs here. Those are actually not galaxies in the cluster, it turns out. These are galaxies that stand behind the cluster, and their light is being gravitationally lensed by all the mass that is there in the cluster. And from these arcs and their analysis, one of the things that we've learned is that actually there is a lot more mass in this cluster than even all these galaxies put together. Even all the galaxies that are put together here only make up maybe 10% or so of the total mass of the cluster, or even less. And most of it is made up by a giant dark matter halo that kind of permeates the space between the galaxies here, in total with a mass that can exceed 10 to the 15 solar masses in the most massive examples like this one here. And there's a range of reasons why these massive dark matter halos are interesting. For example, they can give really detailed clues about cosmology, about the nature of dark energy, about how our universe has grown over the last 13 billion years. But the main reason why I'm interested in them is that the actual galaxies that are sitting in this cluster are also very interesting to study and actually are quite peculiar in a way. And to show this, let me now contrast the galaxy cluster I just shown you on the right with a more typical region of the universe on the left now here. They've just got one single galaxy floating alone, fairly isolated in space, as most galaxies that are there in the universe tend to do. And you can see straight away, just by visual comparison of a typical galaxy that we have in the cluster here to the isolated galaxy on the left, that they are very strikingly different in many of their properties. To just highlight the obvious here, the isolated galaxy has a very blue color. It has these beautiful spiral arms that sit in a flat disk, whereas the cluster galaxy has this very red color coming from the fact that most of its stars have formed a long time ago. It has not formed stars in recent years, or in recent mega and giga years even. And its shape is also very different. It doesn't have any nice spiral arms. It's got more of an elliptical morphology. And so these galaxies are very strikingly different. And most of the galaxies that we see standing together in the cluster really are not just isolated galaxies that for some reason have come together. Somehow the being in the cluster really has a profound impact on how galaxies form and evolve. Now, that's not just something we can see from comparing images like I'm showing here now. We've done lots and lots of studies over the past 4 or 5 decades by now to really try and quantify these differences in detail. And I could almost give a separate seminar on just listing all the various quantities that have been found to change between field and cluster galaxies. I'm not going to do this. I'll just show you one plot here that shows in a quantitative way one of the most important difference that we know about, and that is the difference in star formation activity between isolated and cluster galaxies. This is from a paper a few years ago from the Gamma survey by Luke Davies et al. And what's shown here is on the x-axis the stellar mass of galaxies in solar mass. So from small galaxies less than the Milky Way on the left to very massive galaxies on the right. And what's shown on the y-axis is the passive fraction, so the fraction of these galaxies that is currently not forming stars anymore. And you can see two things here. First of all, the passive fraction increases very systematically with stellar mass, in the sense that more massive galaxies are much less likely to still be forming stars. But at any given stellar mass, there's a very clear difference between whether a galaxy is a central, so an isolated galaxy like the one I'm showing on the left here, and these are shown in red here, slightly confusingly. These are much less likely to be passive than satellite galaxies in a massive halo shown in blue here. So at any given stellar mass, there's a very clear and highly statistically significant effect that clusters essentially stop forming galaxies from forming stars. And I said this is only one of the properties that we have studied. There's been lots and lots of studies trying to understand what is different in cluster galaxies compared to the field. I'm just listing a number of them here to really convince or give the impression that there are actually lots of properties that have been shown to be different. They range from star formation, as I've shown before, in morphology, to H1 content, metallicity, and even the sizes of galaxies that have been shown to be different in clusters and in the field. And there are two more high-level facts about many of these differences that are worth highlighting. And that is firstly, that these are not just differences that we see in the local universe, even though that's where we've studied them in most detail. We now know that many of these differences persist across at least half the age of the universe to redshift 1 and possibly even higher. It's just that it's very hard to study galaxies at even higher redshift in such detail. And we also know that it's not just in the center of these very massive galaxy clusters, like the one shown here, that we see these differences. They also extend to the edges of clusters and even to smaller halos, such as galaxy groups. And so it's really something that affects a sizable fraction of all galaxies in the universe, these differences in the large-scale environments that affect the properties of galaxies. And so we would really like to understand what is going on. Why do clusters affect the way in which galaxies form and evolve? Now, if you ask a question why, then usually someone will come up with theories as to why, what could happen to these galaxies, what could make clusters special. And because it's been a few years since these differences were first observed, there have been lots of different theories proposed about what could be going on here in principle. I'll just briefly highlight 4 of the sort of most prominent ones and most plausible suggestions of what could be happening here. The first is that as a galaxy falls into a massive halo, i.e. a cluster, it changes in the way that it can accrete mass from its surrounding environment. Isolated galaxies are fed by filaments, and they bring in mass and gas that continue feeding the galaxy and support future star formation. That isn't necessarily happening anymore once the galaxy joins the cluster, because then these filaments are effectively redirected and feed the cluster instead of feeding the galaxy. And so this cutoff could have some effect on how the galaxy evolves later on. Secondly, we might go one step further and not just stop the galaxy from accreting more gas, but we might actually be able to strip out gas that is in the galaxy already to begin with. That's a very widely studied mechanism called ram pressure stripping, essentially comparable to the headwind you have when you ride on a motorbike, for example. And we know from detailed numerical simulations that it has the effect of pushing gas out in the opposite direction of the galaxy's direction of motion effectively, such as shown in this example here from one of the early simulation papers by Stephanie Tonneson, where you can see the low density gas being stripped as the galaxy is moving towards the top in this image here. Now, that only affects the gas because ram pressure stripping is a hydrodynamical effect that pushes the gas out of the galaxy effectively. But remember, a galaxy cluster is also a very massive object, and massive objects give rise to strong tidal forces as well. And these tidal forces act indiscriminately on all types of matter in the galaxy. And so tidal forces might also be able to deform and strip gas, but also the dark matter and the stars from galaxies as they fall into a cluster. Again, that's something that's been shown in simulations to be an effective mechanism that could potentially have a significant impact on how much matter we actually still see in the galaxy, because the rest has been stripped away from it. And finally, we should not forget that these galaxies are not interacting individually with the cluster, but there's lots and lots of galaxies that are falling into the cluster at the same time. And they might also be encountering each other and continuously bump into each other, so to speak. And these repeated encounters between galaxies, sometimes called galaxy harassment, could also potentially tidally or hydrodynamically heat the galaxy and therefore have a profound impact on its structure and its ability to retain its gas. So basically, there's no shortage of mechanisms that might be acting in clusters. And what we would really like to understand is which of these is actually happening and which of these is actually the most significant in driving the different evolution of galaxies in these special dense environments. Now, that is actually quite difficult from an observational side, because, as many of you will appreciate, there are fundamental limits to how much information we can get about galaxies in a cluster from simply looking at it in the real universe. I'm illustrating here 3 of the most fundamental difficulties and limitations that we're facing in this kind of study. First of all, we do not see the full 3D distribution of galaxies. We only see a projected 2D view. And even with the best possible redshift information, we cannot distinguish between radial velocities and distance-induced redshift. So we cannot say, for example, whether this galaxy that I'm highlighting here is actually standing quite far in front or back compared to this massive galaxy here, or is actually physically very close to it. Secondly, there's lots of mass in the cluster that we do not directly see. For example, this region down here appears empty, but we know from gravitational lensing that there is a lot of dark matter in this region. There's also lots of hot gas that would be visible in X-rays. But there's a lot more matter as well that is not directly traceable. For example, cooler gas that is not emitting X-rays and that we cannot directly trace. And so it's very hard to actually be able to see what is going on even in the 2D view. And finally, we obviously only see the cluster at one instant in time. And for any length of time that we could plausibly observe this for, even if it's 10 years, 100 years, or 1,000 years even, the cluster would not appreciably change just because the processes happening in it are happening over millions and billions of years. And so there's no way of observing these potential transformations and these effects actually in real life in a galaxy cluster. And that obviously puts severe limits on our ability to really distinguish these mechanisms that I've just outlined and actually say directly in a fully empirical way what is happening and which of these mechanisms are actually the relevant ones in driving the evolution of these galaxies that we see here. So let me just summarize this first part of my talk that I've just given. Galaxy clusters are collections of a large number, up to thousands of galaxies that stand close together. But it's very important that these are not just normal galaxies. These are special galaxies that have been shaped significantly by their special environment. And although we know that there are a lot of physical mechanisms that could potentially be acting and could potentially shape these galaxies, it is really very difficult and almost impossible to tell apart the action of these mechanisms from a purely observational and purely empirical viewpoint. And that really motivates looking at clusters, not just from observations, but also from a theoretical viewpoint with the aid of simulations. And that's what I'll be talking about now in the second part of my talk here. If there are any questions, by the way, feel free to interrupt or let me know. But otherwise, I'm also happy to answer any questions after my talk at the end. So we need simulations to really understand what is happening to galaxies and clusters and why they evolve the way they do. And simulations is a field that has evolved really dramatically over the last 5 to 10 years. And I, again, could give a whole seminar on just reviewing the different techniques and different approaches that have been used in this field. For simplicity, I will just narrow my approach down to one particular simulation suite that I have mostly worked with in my research, and that is the Eagle simulation suite. developed a few years ago in LADER by Jellyfish and collaborators. Here's a visual impression of what the main simulation from this project looks like in the big box on the left. What is shown here is the gas in a 100 megaparsec region of the universe simulated with what's called smooth particle hydrodynamics, basically meaning we simulate gravity, but also the effects of gas physics, such as pressure and the temperature increase and how the gas reacts to this. And you can see that there's a vast range of structures from hot gas, shown in red here, that populates the dense regions, such as galaxy groups and clusters. But then as we zoom in successively, the simulation does actually reproduce objects that look quite significantly like real galaxies, like the one shown here in the topmost zoom in here. And to achieve this, it's important to realize that these simulations have a limited resolution. There is a limited ability of them to resolve structures that are there in the universe, just because otherwise we would need infinite computing power, and that's something we do not have. In the case of Eagle, this resolution is at the scale of about 10 to the 6 solar masses in mass, or about a kiloparsec, just below a kiloparsec in spatial scales. And that means that a lot of properties that we know are important in the real universe cannot be self-consistently captured by these simulations. Just as one example, we know that stars are formed in regions like the Orion Nebula that are much smaller than 10 to the 6 solar masses. It's probably of the order of 1,000 solar masses for the entire nebula here, and obviously much, much smaller for the individual regions where stars actually do form. And so there's no hope for the simulation to include and model these processes self-consistently. We have to put them in by hand, and that's done in what's called a subgrid physics approach. So essentially we say, we know if gas on resolved scales has certain properties, like a certain density, a certain temperature, a certain metallicity, then empirically it will form stars at a given rate. And that's a recipe that can be put into the simulations, even if it is not directly resolved, to give the simulation the ability to model these crucial processes. For example, star formation, but also the supernova feedback that results from it, or analogously, feedback from massive black holes that are sitting in the center of massive halos, and so on. And it's really the implementation and calibration of these subgrid physics recipes that has given simulations in the last few years the ability to produce galaxy populations that look quite remarkably like the real universe. To show one example of how good simulations of this kind are nowadays, here are the two main calibration diagnostics that the Eagle project used. It's on the left-hand side, the stellar mass function, so how many galaxies there are at a given range in stellar mass. You can see that it decreases towards higher stellar mass, so more massive galaxies are less common. And in comparison to the observations, which are shown in gray here, the simulations do a really good job. These are three slightly different variants of the Eagle model, but they all follow the observations very, very closely, and certainly much better than previous generation simulations that had been around even 10 years ago. And secondly, the sizes of galaxies as a function of stellar mass, as shown on the right here, for the reference model shown in blue and yellow here, also do agree very closely with what the observational constraints are telling us. And so it does a very good job on reproducing these properties that the model was explicitly calibrated to reproduce. But obviously that's kind of only half of what we want. We don't just want a simulation to reproduce what we put in, so to speak, but we actually want to get some insight and some useful information on things we have not put in directly. And one thing that is really satisfying this bill exactly is galaxy clusters, because the Eagle box, I've said, is 100 megaparsec in size, and that is quite a large volume. But compared to the scales of the universe and the typical density of galaxy clusters, it's actually not a very large volume at all. And as a result of this, the number of halos that are resolved in or contained in the 100 megaparsec Eagle volume decreases very drastically as we go up in halo mass. That's what I'm showing here. So on group scales with halo masses of, say, 10 to the 13, a few times 10 to the 13, their Eagle has dozens to 100 objects, and it's really well modeling this regime. But on massive clusters, we really are limited to, at best, a few objects in sort of the low mass cluster regime. Something like maybe the Virgo cluster, we have a handful of analogs or so, but certainly none of the more massive objects like the one I had shown before. For reference, the Abell 370 cluster that is actually even sitting at a slightly higher redshift, which makes the problem worse, is sitting somewhere here. So quite a far way off from where a simulation like Eagle would actually be able to tell us something. So what can we do? If these objects are not in our simulation, we obviously cannot study them, and the whole simulation is in a way pointless. But there is an easy way to solve this problem, and that is just to go to a larger volume, right? Because if the limited volume is the crux of the problem, then we can just make the volume bigger, and just by statistical power, we will get these rare massive clusters in the end. And that's what I've done in the Hydrangea simulation project. We've gone to a very, very big box, and this is 3.2 gigaparsec in size now. For visual reference, here right in the top corner, this is the Eagle 100 megaparsec box from before. So now we're much, much bigger. And we have over 100,000 galaxy clusters in this box here now. So a vast increase in number statistics. This comes at a price though, and it's a very significant price. The resolution that we can afford in such a big box is absolutely pathetic. It's at the level of 10 to the 12 solar masses per particle, so one whole particle per galaxy. And we really cannot say anything really from this apart from where a galaxy cluster is going to form. But that is already a useful information, because it means if we know from this simulation where a cluster will form, we can run the simulation again, and we can concentrate the computing power in these small regions where we know something interesting is going to happen. And we can therefore effectively simulate these rare regions that are only formed in massive boxes and large boxes with the same physics and the same resolution as we have done in Eagle before. And that then allows us to actually get very nice details simulated of these massive halos. Here's the same one I had shown you before, now from the Hydrangea simulations. You can see that it's not just one diffuse blob, but we actually see a large variety of structure. We see a hot gas halo in the center, surrounded by filaments that are feeding it in, and a large number of substructures that are sitting in these filaments, all of which is just completely unresolved and unmodeled in the parent simulation. It's still an expensive thing to do. It cost in total about 50 million CPU hours to run these simulations, 24 of them in total. But it's at least feasible. I mean, running the entire box at this resolution would, I don't know, have taken hundreds of years and be absolutely out of the question. So it's kind of the best we can do. And as I'll show you, it's actually very, very good and very useful what we can do with these simulations. I'll first briefly show you what it makes now to our ability to resolve massive halos. Showing again the plot of the halo mass function now from Hydrangea. You can see that it extends now to much higher masses. We have on the mass scale of Virgo now dozens of objects, and even about 10 as massive as the Coma cluster. And even the most massive ones are almost now in reach of these very, very massive Hubble frontier fields clusters. So it's really a very significant improvement in terms of mass scales that can be simulated now with these so-called zoom-in cluster simulations. And I hope that this is coming through to some extent over the Zoom link here. I just want to show you a visual impression of what this giant dynamic range that we have in these simulations actually means. This is a fly-through through one of the most massive clusters we have simulated, starting from the very large outskirts and now zooming into the inner regions where we then see individual galaxies embedded in this whole network of gas that permeates the cluster. Here just frozen for one point in time, but obviously in the simulation, we also have the entire evolution of these galaxies and can actually trace what's going on. And secondly, we don't just have the gas. As I've said before, the simulations include subgrid physics models for how to transform this gas into stars. And so we can also simulate or predict how this cluster would look like if I observed it in a telescope. And it looks, at least to first order, pretty much like we would expect. There is a collection of many, many hundreds or thousands of galaxies with morphologies broadly reflecting the variety in morphology that we see in the real universe. So to sort of first order, it all looks nice, and the simulations do look a bit like real clusters at least. So let me now take this one step further up and actually analyze what the simulations are giving us in a more quantitative sense. And that's now from a series of comparison works that we've done over the last few years. Let me first show you the gas fraction that is contained in the cluster that's shown here. So on the x-axis, I'm showing the total mass of the cluster. And on the y-axis, what fraction of the mass within R500, sort of a typical region radius of the cluster, is actually in the form of gas. The black points are observations, and the red points are our cluster simulations. So you can see that they are broadly in the right ballpark. They are below and reaching up to the cosmic mean at high masses. In detail, they are slightly on the high side by a few percent. So our galaxy clusters do have slightly too much gas in them. And it turns out this is probably because the AGN feedback that we put into the simulation is not quite effective enough at blowing out the gas from these clusters, especially at high redshift. And that's something that we clearly need to improve on in future models to actually bring the predictions into agreement with what we really do see in the observations. Something that's looking significantly better, actually, is the stars in the galaxies, though. I'm showing here the stellar mass function again, similar to the calibration plot from Eagle, but now in terms of what we are seeing in galaxy clusters after all these environmental effects have modified the way in which galaxies are formed. And you can see that both at redshift 0, effectively, and redshift 1, the observations agree very well with what the simulations are actually predicting. The observations here are shown as symbols in the top panel and the simulations as lines for slightly different definitions of how we select galaxies. And they, in all three cases, agree very well in the local universe. And also my student Lami Mahat did a comparison for this now to newer observations at redshift 1, where we now have detailed mass functions as well over a fairly wide range in stellar mass. And again, the simulations predict a very realistic distribution of stellar masses across almost 2 decks in stellar mass in these massive clusters. So that's nice. We get galaxies that don't just look approximately realistic, but they do actually also have about the right amount of stellar mass. Now, what about the ability of the simulation to actually form, or the galaxies in the simulation to form new stars, though? So how many galaxies are passive? Remembering the plot I had shown right at the beginning with this big difference in passive fraction between field and cluster galaxies. So this is what I'm showing here now. On the x-axis is now the stellar mass of the galaxy, and on the y-axis, the quenched, the passive fraction. And I'll build this up by first showing just the field, so just isolated galaxies, simulations as lines and observations as symbols here. And again, you can see it's broadly realistic to 0th order at least. They increase significantly with stellar mass in both cases, although the simulations are not quite perfect. In particular, at high mass, the quenched fraction is slightly too low. And we think, again, this is probably a result of AGN feedback not quenching these galaxies quite efficiently enough. So in a way related to the high gas fractions that we had seen on the cluster scales before. But what's really interesting now is to contrast this with what we see for satellite galaxies, so not for isolated field galaxies. And that's shown here now in this comparison, where the different non-blue lines now show the simulation predictions for the satellite galaxies of the same stellar mass compared to observations in the same halo mass bands. And we see that there is indeed a very significant increase here in the sense that the cluster galaxies are quenched to significantly more than 50%, up to almost 100% at the low mass end here. And in fact, it might even be slightly too high if you compare in detail the observations shown as points here, especially on the low mass scale. The simulations actually, by the looks of it, quench galaxies even slightly too efficiently. So there's definitely something happening in the simulations, but it's maybe a bit too much of the something that is actually going on there. This is at redshift 0 approximately. Again, in recent years, it's been possible to do these comparisons from the observational side at high redshift as well. This is a plot from a recent paper by Egidius Kukstas, where he compared the Hydrangea predictions and also from some other simulations to data from the Go Green survey. And you can see that this offset, especially at the low mass scale, that all the simulations essentially tend to predict quenched fractions that are above what the data are telling us, is really persisting at high redshift. And it's something that's not just specific to our specific simulation model, but it seems to be a more common issue that most simulations, or at least the ones that are shown here, suffer from this problem that they remove or that they shut down star formation somewhat too efficiently. And that's something I'll come back to shortly at the end of my talk. Now, let me again just summarize briefly what I've said so far about simulations and Hydrangea. It's a suite of galaxy cluster zoom simulations that's based on Eagle to extend Eagle effectively to these very massive cluster scales that we do not have in the original Eagle periodic box simulations. And in most respects, it is achieving a very good match to what we see observationally, for example, in the stellar masses of galaxies. But something such as star formation, especially in low mass galaxies, appears to be shut down slightly too efficiently compared to simulations, to observations. So it's a good start in a way, but there's certainly still room for further improvement in the simulation models. So you can either take this now as, okay, we have a nice tool to do something with, or everything is doom and gloom and the simulations are not perfect, so let's throw them in the bin and start from scratch again. For the next and last major part of my talk, I'll take the first approach and argue that even though these simulations are not perfect, there are actually some really interesting science insights they can give us on what's happening in the real universe, especially if we tailor these kind of science questions to the properties that the simulations are actually getting well and are actually reproducing pretty accurately. And one of the things that it does well on, I've said, is the stellar mass distribution that is there in the clusters and in their satellites, for example. And what that allows us to look at is a really interesting science question, namely how these stars that are there in satellite galaxies in the clusters are potentially redistributed from the satellites into this diffuse halo called the intracluster light that we are now observing in more and more galaxy clusters in the real universe. Here's one figure that shows it very clearly from the Hubble frontier fields in a special processing by Mireia Montes, where you can clearly see that the space between the galaxies is not actually empty and not actually dark, but there is this diffuse ghostly glow of stars that permeate the space between the galaxies. And actually our simulations show something fairly similar. There's also this extended halo of stars around the brightest cluster galaxies. So what can we say from our simulations in terms of where this comes from? Are these stars that somehow formed in between galaxies? Is star formation not limited to galaxies as we have thought before? Or is there something else going on that could explain why we have these stars floating around in the cluster itself instead of being bound to galaxies? Now, let's start this at a qualitative level by just looking at what is happening in the simulation, because I've said before, one of the nice things about a simulation is that we do not have this limitation of being limited to one frozen point in time. We can actually see what has happened over almost the entire age of the universe. And if we save enough outputs, we can just make a movie effectively of what the assembly of a galaxy cluster looks like. And that's what I'm showing here now on the left-hand panel. This is one of the simulated galaxy clusters assembling from very high redshift, started at redshift 3 or so. Now we've reached redshift just about 1. And you can see that there's lots of galaxies falling into the cluster. And as they fall in, many of them do indeed shed significant amounts of stars from them through tidal stripping. That then, presumably, is what's forming this diffuse halo that is actually starting to grow here. And now at redshift 0.5 is actually quite a significant feature and a significant component of the cluster already. Now, does that also work quantitatively? Is what we're seeing here sort of visually actually what's happening? Or is there something more that's going on than stars being stripped from infalling satellites? Now, to do that, let's do the actual analysis and let's see what is actually happening in a quantitative way in the simulations. And what I'll show here first now is how many stars, or what fraction of the stars to be more precise, is actually stripped from galaxies as they fall into the cluster. We can do this. We can just follow all the galaxies in the simulation from the point when they fall into the cluster to redshift 0. And then I can now say, as a function of their stellar mass, of galaxies in a given stellar mass, what mass have they lost between the time when they had their peak stellar mass and redshift 0. So that's what I'm showing here now. It's on the x-axis, the mass loss, and on the y-axis, the fraction of galaxies that have experienced at least this mass loss. So it's effectively a cumulative distribution function here shown, right? So if I'm looking at this for Milky Way-ish like galaxies with a peak stellar mass of 1 to maybe 3 times 10 to the 10 solar masses, then the distribution looks like this. Very, very strongly peaked towards very little stellar mass loss, Keep in mind this year is at about 10%, so really not very much mass that these galaxies have typically lost. There are some that have lost even less, and then there are a few, sort of the most extreme ones, that have actually lost a bit more, sort of up to 30, 40, 50%. In some very, very rare cases, even more. Now that's just for one bin in stellar mass. If we do this for a whole range of masses, from tiny dwarfs up to more massive galaxies, we do see some variation with stellar mass here, yes, but by and large, the picture kind of remains the same, that galaxies typically do not lose excessive amounts of their stars. We do not see stellar losses of the order of, I don't know, 80, 90%. It's more sort of in the 10, 20% more typically. So a little bit of stellar mass loss does occur, but it's not very significant. Now there's one subtlety here though, and that is that I can only make this plot for galaxies that I still have there at redshift 0. Because if a galaxy doesn't even survive to redshift 0, I cannot put it on this plot here. It would essentially show up as infinite mass loss. And this is something that could also potentially happen, that a galaxy comes in and is just completely disrupted or completely merged by its tidal interaction with the cluster. Now, to see how frequently that is happening, let me show you another plot in a slightly different setup here. So what I'm showing here on the y-axis now is this fraction of galaxies that is surviving from infall to redshift 0. And I'm showing this for clarity on the x-axis against the time when the galaxy actually was accreted onto the cluster. Because that clearly has an impact, right? I mean, if a galaxy has only just been accreted at redshift 0, it cannot really have had much time to be destroyed. It should really be surviving until now. Whereas if it had been accreted almost at the beginning of the universe, it's had a long time in the cluster for bad things to happen to it effectively. And sure enough, if I now look again at this in a narrow range of Milky Way-like peak mass ranges here, it starts off very high, and then it actually stays very high, essentially at almost unity back to redshift 1 and slightly beyond. And it's only really galaxies that have been accreted very early on in the first half of the universe that have any significant rate of being completely disrupted. Effectively, you can turn this around and say any galaxy that has come into the cluster since redshift 1 is still there today. And again, this is shown for one range in galaxy masses initially now, but it looks fairly similar across a broad range of masses. There's a slight trend in that more massive galaxies show more disruption later on. That may seem counterintuitive in a way, that it's these tiny, tiny galaxies like tiny dwarfs that seem to be able to survive in the cluster for the longest. But it turns out this is because of dynamical friction. Massive galaxies experience strong dynamical friction that drag them to the center of the cluster. And the tidal force goes as r to the -3. So the tidal force is really very strong in the center. And being dragged to the center by dynamical friction really makes massive galaxies much more susceptible to being disrupted. So disruption does happen, yes, only to galaxies that have been accreted very early on, but it does happen. And this obviously would then liberate a large number of stars that could potentially go into the ICL and the BCG as well. So what is it? Is it that these stars were formed in their place in situ already? Were they stripped from satellites that came in, or were they ripped out from galaxies that disrupted completely? So there are three possible ways in which the ICL could have formed in principle. Now let's see what's actually happening in the simulations. And I can do this because I can essentially address the question the other way around now. I can say, I'm looking at what's there at redshift 0. Then I have the galaxy cluster halo like this. And I can now say, where did all these stars come from directly? The first thing I have to do for this, and that's something that observers are much more struggling with than simulators, is to take out all these satellite galaxies now that are almost polluting the image here. I can do this very easily in the simulations because I know what the dynamics of each resolution element is. So I can identify essentially what the smooth background component is. And I can then go one step further and say, I'm not just looking at this as a smooth component of mass, but I can actually break this down into the individual stellar particles that make up the simulation at its most basic level. And these particles I can trace over time. And so I can say for each of these particles with a mass of about 1 million solar masses, as I've said before, for each of these particles, I can say, where did it come from? How did it actually get to where it is now? And specifically, as a first step, was it formed in situ, so in the cluster already, in its location? And these ones I'm coloring in blue here. Or was it brought in from another galaxy and stripped out of this galaxy? And those ones I'm showing in orange here. And well, visually, you can already see orange clearly dominates in this plot here. So most of the stellar mass shown in this tiny patch here was actually brought in from other galaxies, so accreted ex situ. And again, we can do this not just visually, but also in a direct quantitative way by showing how this in situ versus ex situ fraction varies across the radius of the cluster. So that's what I'm showing on the x-axis here, the fraction of stellar mass that was brought in by these two different channels. And indeed, you can see in situ is always subdominant to ex situ. So yes, there is some star formation happening in the cluster that creates stars that are sitting at 100 or even 1,000 kiloparsec from the center. But the vast majority of these stars were clearly brought in from other galaxies and were then stripped by tidal forces. And now to answer the question of what kind of stripping brought the galaxies there, was it gentle stripping from galaxies that are surviving to today, or really these disruptive events that caused the galaxy to be destroyed completely? Well, again, we can just break down the top line here into these two categories. And it's a very revealing plot because there's a clear bimodality here in radius. You can see that stars that are sitting near the center of the cluster, out to maybe 50 or 100 kiloparsec or so, these were very predominantly, almost exclusively brought in by galaxies that merged and got disrupted, and so that aren't there anymore. Whereas stars on the outer ICL, this really faint extended halo, these were in their vast majority brought in from satellites that are still there today, but that were stripped from their satellites in these small but evidently cumulatively efficient stripping events that affect galaxies slightly. And finally, we can also ask the question of what galaxies did these stars actually come from? We can not just say these were stripped from galaxies, but we can ask what stellar mass, for example, was the satellite that these stars formed in. That's what I'm showing here. Again, as a cumulative distribution function, as a function of stellar mass in which these stars were formed. For simplicity, I'll start with just the very central region of the cluster, so really the innermost part of the brightest cluster galaxy, the BCG. And for those in the simulations, it's a very homogeneous population almost. Essentially, all of these stars were formed in very massive galaxies, more massive than the Milky Way, effectively, around 10 to the 11 solar masses or so. But that changes dramatically if we go out further into the outer realms of the outer ICL. And in that case, we really see that there's a very heterogeneous mix of stars, from those that were formed in tiny dwarfs, essentially, that are hardly resolved in the simulation with 10 to the 7 solar masses or so, all the way up to really massive galaxies, way more massive than the Milky Way. So the BCG, yes, is fairly homogeneous according to the simulations, formed in massive galaxies, but there is no such thing as a typical progenitor population of the ICL. It's really a very heterogeneous mix of stars formed in a vast variety of galaxies that was then stripped to actually form this diffuse halo. Now, let me summarize again this point about the origin of the BCG and the ICL. I've said that according to the simulations, typical surviving satellites only lose a fairly small fraction of their stars, of the order of 10 or maybe 20%. Some satellites are also disrupted completely, but it's really only the ones that have fallen in very early on. Disruption is only effective for these early accreted galaxies, not for later on ones. And in terms of what builds up the stellar halo of clusters, the BCG, the center, is built up from these few disruption events of galaxies that were accreted early on. Whereas the outer ICL is sort of the amalgamation of stars stripped from these various outer stars that were stripped from many of the galaxies that fell into the cluster. All right, so I hope I have 5 more minutes or so maybe in my talk to give you a brief outlook of where this work will be going next. And for this, it's a good point to come back to one of the plots that showed that the simulations are not actually perfect, namely the one of the quenched fraction of galaxies. This here is a slightly updated version of the plot I'd shown you earlier, now extended to lower stellar masses, with new data that had been derived from Stripe 82 and SDSS that really clearly show that there is a discrepancy between what the simulations predict in terms of this very high quench fraction and the level indicated by observations. And we would like to understand where this is coming from. Why exactly are the simulations shutting down star formation too efficiently? And again, for this, it's a useful approach to understand what is actually happening. In which way is the gas that fuels star formation driven out of galaxies in the simulations? And I'm showing here again an animation, a video of one individual galaxy as it is forming now as a nice spiral disk. And now very soon it will fall into the cluster. It now encounters the hot intercluster medium. And you can see that as soon as this happens, there's really a dramatic change to the gas, well, disk of the galaxy. It loses almost all of this essentially instantaneously. And after only one pericentric passage, there's a tiny, tiny bit of gas still left in the center, but really not enough to sustain any significant star formation. And as it now approaches the cluster for a second time, even this small amount of gas is easily stripped and removed. So gas stripping is evidently very effective in removing gas from infalling galaxies in the simulations. And this is not just something that's happening in this one galaxy. We see this ubiquitously, essentially, whenever we look at infalling galaxies in the simulations. And it's also something that we actually see in the real universe. These so-called jellyfish tails are something that we see in some cases happening in reality, but evidently whatever is producing them in the simulations is just too efficient. So being able to drive the star-forming gas out from the simulations is too easy, or in other words, the gas is just not tightly enough bound to the galaxy in order to withstand this ram pressure for long enough to be in agreement with what the observations are telling us. And it turns out there is actually one fairly appealing explanation for what might be causing this. And it can be seen by looking, as the last plot of my talk, the temperature density diagram of gas that we're seeing in the simulations. So this is temperature of individual gas particles on the y-axis versus the density of these gas particles on the x-axis. And there's a lot of structure in here, again, that I do not want to go into. But one feature that is very suspicious, let's say maybe, is this very abrupt cutoff at the lower right edge here towards cold, dense gas. And dense gas is exactly the gas that is most able to withstand ram pressure stripping. And where does this cutoff come from? It turns out it's actually put in by hand explicitly to prevent gas from reaching this regime, because we cannot model it with the way the simulations are set up at the moment. There's no way to properly resolve this cold dense phase with simulations like Eagle. But it clearly suggests that resolving this is something that will give significant progress on the question of how galaxies are evolving in clusters. And it's something that we've been working on for the last several years now, and we will soon have a new generation of simulations that will actually push the temperature density diagram fully into the cold molecular gas phase region. And it'll be interesting to see how this then changes the predictions of the simulations in terms of the gas and the stripping of star and quenching of star formation in clusters, and whether this resolves the issue, or if there is actually something more fundamental that's going wrong in the simulations, which could also be the case. For now, I'll end here. I'll leave you with my 3 main points as a summary. So first of all, I've introduced the Hydrangea simulations, spin-off of the Eagle model, focusing on simulating massive galaxy clusters. I've shown that most of the predictions from the simulation are broadly realistic, and that they allow us to do some interesting science, for example, understanding where the stars in the brightest cluster galaxy and intracluster light come from. And finally, just now, I hope I've convinced you that even where simulations are showing failures and they're not actually realistic, we can still learn some interesting science from them, and especially in showing us where this should go next and where improvements could actually make scientific improvements. So I'll leave it here. Thank you very much for your attention. If there's any questions, please let me know.